Hello, this is Scholar Strive doing some math. Today we're going to be looking at perpendicular bisectors. So remember, perpendicular means they intersect to form right angles. Bisector means they get cut in half. So let's say we have a line, and then we have a segment. Let's call this AB. And we have another line called the perpendicular bisector. And it splits it in half. So DM is the perpendicular, remember perpendicular is that side, bisector of AB. Okay? Perpendicular bisector also makes right angles. So 4 right angles there. Alright, perpendicular bisector theorem. So what this says is if a point is on the perpendicular bisector of a segment, then that point is equidistant to the endpoints of that segment. So what they're saying is, so let's do this again. So let's look at AB here. And this is the perpendicular bisector. So if there's a point on the red line here, then it is equidistant. So if you wanted to measure the distance between here, let's call this D, and here, it should be the same. So AD is congruent to DB. Okay. If I put another point, it should be still the same thing. Let's call this C. AC should be the same as CB, as long as it's in the perpendicular bisector. And then it works backwards. If a point is equidistant, so I'm going to use that same picture and just say it backwards. So if AD is congruent to DB, then this point, and then D is on the perpendicular bisector. Okay. And then this extra perpendicular bisector theorem says if 2 points are each equidistant, so let's say D and C, you can connect them and create the perpendicular bisector. So if D and C are both equidistant from A and B, then you can create your perpendicular bisector. Concurrency. Concurrency is when 3 or more segments, lines, or rays meet at a single point. So let's have one line here, one line there, and then one line here. Oops. I almost did it. There. So we have 3 lines, or it could be rays, or it could be segments. 3 more intersecting at this point. This is called the concurrency. Let me use a different color. Concurrency. It's just the intersection of 3 or more things. Okay, concurrency of perpendicular bisectors in the triangle. So triangle ABC. If you took the three perpendicular bisectors, so if I started here, went 90 degrees, and split this in half. If I started from here, and went 90 degrees and split this in half, and if I went here and split this in half, these would all intersect at a point, and that would be the concurrency of the perpendicular bisectors. It's called the circumcenter. Okay. And basically it's the center of the triangle. It's equidistant from any of the three corners. Alright, example 1. AC is a perpendicular bisector of BD. Okay. So that gets split in half here. That means point A is equidistant from B and D. So that means 7x minus 6 is equal to 4x. So I'm going to subtract 4x over, and I'll get 3x minus 6 equals 0. I'm going to add 6 to both sides and get 3x equals 6. So finally we divide by 3 and get x equals 2. Okay, find AD. AD is 4 times 2, which is 8. Example 2. In the diagram, KN is perpendicular bisector of JL. Okay, that means these are the same, and these are the same. What segments lengths in the diagram are equal? Oh, well, okay. So JK and KL, JN and NL. Okay, those are the only ones we know for sure. Now they ask us, is point M on KN? So if we continue KN and keep on going, does M fall on that line? How do we figure that out? If JM is equal to ML, which they are, then it does lie on that line. Because if a point is equidistant to endpoints of a segment, then that point is on the perpendicular bisector. And that is, right here, the converse. If a point is equidistant to the endpoints of a segment, then that point must lie on the perpendicular of the on the perpendicular bisector. Okay, so you need to show that JM is equal to ML or congruent, and that'll tell you that it is on the perpendicular bisector. Alright, use the same diagram for checkpoints 1 and 2. So in the diagram, KJ is the perpendicular bisector of GH. Okay, so what segments are equal? GK and KH. So here and here, here and here. GJ and JH. Okay. G. Okay, find GH. So those are split in half. So 2x equals x plus 1. So x equals 1. GH is 2 times 1, which is 2. And obviously, I forgot one more. FG is equal to FH because they're both 4.1. Oh wait, I'm looking for G. Oh, GH. GH is the whole line there. So if one half of it is 2, times it by another 2 to get 4. Okay, given CP is the perpendicular bisector of AB, prove that AC is congruent to BC. Statement. Reason. So given CP is perpendicular bisector of AB. Okay, and that's because it was given to us. So what does that mean? Okay, means a few things. So it means, so perpendicular means right angles, so it makes right angles. So angle CPB and angle CPA are right angles. Okay. And that says if two segments are perpendicular. Then they intersect to form right angles. That is the definition of perpendicular lines or segments. Okay. So we have two right angles here. Okay, we also know that AP is congruent to PB. Okay, that's the definition of a bisector. So if a line bisects a segment, then it divides it into two congruent parts. Okay, so we have a side, an angle, and they both share CP. CP is congruent to CP. Why? Because the reflexive property. I am myself, whatnot. So now we can show that these triangles are congruent. So triangle CPA is congruent to triangle CPB. And that is SAS. Okay, now that we know that the triangles are congruent, we can finally say that AC is congruent to BC because CPCTC. Congruent parts of congruent triangles are congruent. Or corresponding parts of congruent triangles are congruent. Alright, checkpoint 3. Another proof. Here we go. Alright. Statement. Reason. So they tell us, we start with your given. So AB is congruent to AC in circle O. Given. Prove that AD is the perpendicular bisector of BC. Okay. So what do we need to show? Let's go back to our theorems here. So perpendicular bisector. So we need to show either that, it creates right angles and divides the side in half, or divides the thing in half. Or we can show, let's see, if a point, what can we show here? Yeah. Okay. All right. So I'm going to create two lines here. BQ and CQ. Oh, those are, no, that's an O. OB and OC. Okay. Now this one you might not know. I don't really like this proof because I haven't taught you about the circle yet. But in a circle, so this is circle O. O in this case would represent the center of the circle. So if we drew lines from BO to CO, OB would be congruent to OC because in a circle, all radii of the circle are congruent. So basically I made two radiuses, so BO and OC. Radiuses of the circle, they're all the same, so they're congruent. And I'm going to say point A and point O are on a perpendicular bisector of BC. And why? It's because this upper one up here. So converse, if a point is equidistant to the endpoints of a segment, then that point must lie on the perpendicular bisector. Okay, so both point O and point A are both equidistant from B and C. So 3. So I'm just gonna write converse of the perpendicular bisector theorem. So now I can say so I need to show that A, Q, and D are collinear. And the reason why I need to show that they're collinear is because I need to show that they're on the same line. So that's given in the diagram. We're able to assume collinearity from diagram. So now I can say that AD is the perpendicular bisector because of substitution. But basically what I did was, since A, O, and D are collinear, that means you can create the line AO or AD. And since those points are on the perpendicular, or since A and O are both equidistant, they lie on the perpendicular bisector. And since they lie on the perpendicular bisector, D must as well, since they're collinear. So I won't give you a test question on checkpoint 3, because for one, you need to know about the circle. Well, you should know that all radiuses are the same, but you might not necessarily, go to that sort of reasoning. One before that, you should know how to do this. Prove that too, especially if they give you the hint, use congruent triangles. You know that there's SAS, ASA, side-side angle. Wait, is that right? No, that's not side-side angle. So, SSS, SAS, AAS, ASA, HL. That was from last chapter. Alright, let's move on.